Hey guys, welcome back to chapter 14. We are going to continue into chapter 14 with our qualitative look at kinetics. So, what can kinetics tell us about a reaction? And today, specifically, we're going to talk about reaction mechanism. So, chemical reactions are generally described with an equation listing all the reactants and the products. So, up until this point, we've really only shown you a reaction happening one way: reactants, arrow, products, that's it. But in reality, that's not how chemistry actually takes place. It's not a B kind of reaction. Most reactions occur in a series of small reactions involving one or two or at most three molecules at a time. So this is something that you'll study at length in organic chemistry if you're moving on to organic chemistry. But for now, we're just going to briefly introduce this idea of a reaction mechanism. So this small series of steps that when added together leads to one big reaction that we typically depict on the screen. So a reaction mechanism describes the series of reactions that occurs to produce the overall reaction that we're interested in, or the overall reaction that we observe on a macroscopic level. Okay. So kinetics can help us piece together these small little reactions that happen along the way. And if we know how a reaction takes place, so we know all the little steps along the way, that's invaluable knowledge as a chemist, because if we know how it happens, then we know exactly how to manipulate it. So create more of something or less of something, speed it up, slow it down, whatever it is we're trying to do. So reaction mechanism, what we're going to do is we're going to piece together the possible mechanism by working backwards through the kinetics data. So we're going to take a look at the kinetics data. We're going to kind of piecemeal it together. It's going to give us one piece of the puzzle when trying to figure out what's going on with a reaction mechanism. Okay. So we're going to look at a detailed description of what happens at the molecular level. And as I alluded to, this is very highly sought after information knowledge. So how are we going to piece together this kinetics data? What we're going to look at is what's called a rate limiting step. So this happens in a series of steps. A reaction happens in a series of steps. And one of the steps is going to be the slow step or the rate limiting step. Okay. So let's think about an example of what would affect a rate that we're familiar with. So let's say that we want to talk about going from Wilmington to Raleigh, right? So depending on where you're going in Raleigh, that takes roughly, 2.5 hours, right? So if all lanes of traffic are open, no accidents, no construction, we can get from Wilmington to Raleigh in, let's say, 2 hours, okay? But what happens if there's construction somewhere? What if there happens if there's construction along the way, or when there's construction along the way? We know how that goes, right? So where there's construction might be a 2-mile area where they're working on that road. Well, the road goes from a 3-lane road down to a 1-lane road, right? And when it goes down to a 1-lane road, traffic gets slowed down. So that 2-mile stretch is going to be the rate determining step for your journey. So going from Raleigh to Fuquay, going from Wilmington to Fuquay, clear, open, clear sailing. Once you hit Fuquay Varina, there's 2-mile stretch where it's down to 1 lane. That's going to limit you from going any faster. And then after Fuquay Varina to your destination, wide open, traffic's open, we move fast. That little 2-mile stretch is going to be your rate determining stretch or your rate determining step. That's going to slow everything down. And how long you're in those 2 miles of the 1-lane road is going to determine how long your trip's going to take, right? So that's going to determine how fast you can get there. Okay, so that's the kind of thing that we're going to be looking at. We're going to look at these series of steps. We're going to determine our 2-mile stretch, or we're going to determine where our reaction slows down. And then we're going to try to piecemeal the rest of the reaction together to get our rate equation, to get the rate of that reaction. So here's an example. This is the kind of reaction that we would depict lately on the screen. So we've got hydrogen reacts with this ICl to produce hydrochloric acid and iodine out on the other side. So here's our reactants, here's our products, and it's that easy, right? Well, no, not so much. So this is what we've been depicting. Reality is a much messier situation. So here we see reality. So the reality is this happens in two separate steps. We call them elementary steps. So step one is that this hydrogen will react with one of these molecules of the ICl and will create hydrochloric acid and hydroiodic acid. Okay, so we're creating the hydrochloric acid, which is what we want in the end, but this hydroiodic acid is it's called an intermediate. Okay, it's not in the overall reaction. And then a second elementary step, that hydroiodic acid, which is pretty unstable, reacts with another molecule of this ICl. And the result of that is another molecule of hydrochloric acid, and then we see that iodine spit out on the other side. So step one, step two, we get our overall reaction. So a couple of things to point out here. I've already said the words, but I want to make sure that I'm very clear about it. A couple of things that we want to point out here is first our intermediates. So this hydroiodic acid is an intermediate. So an intermediate is something that is produced in one step. So we produce it here in step one, and then immediately consumed in the next step or a later step. Okay, so we start to pile up this hydroiodic acid, and then immediately that hydroiodic acid starts to react. And so we produce it, then we consume it all at the same time. We also will not see intermediates in our overall reaction. So if we produce it and then immediately use it, we're not going to have any left over at the end, right? It's going to be used up during the reaction. So intermediates are also not going to be found in our overall reaction. So if we look back up here at the overall reaction, we don't see the hydroiodic acid anywhere because it was used up. To get to this overall reaction, we add together our two elementary steps. So what does that look like? How do you add together chemical reactions? So when we add together chemical reactions, the first thing that we're going to do is identify our intermediates. So this hydroiodic acid is an intermediate. I can cancel those out. They're not going to be in the overall. Okay. Once I've identified intermediates and then later on catalysts, we go ahead and just add together everything that's left. And I always separate it by the reaction arrow. So we've got reactants and we've got products. So left on the reactant side, we've got hydrogen from elementary step number one. And we've got this ICl from elementary step number one. So that's it from that step. And then the second step, we've got this ICl as well. And we'll clean that up in just a minute. So that's everything on the reactant side of the arrow. Now if we go to the product side of the arrow, I see hydrochloric acid from step one, hydrochloric acid from step two, and iodine from step two. So all I've done here is I've gotten rid of the intermediates and I've added up everything that's left, okay? We can reduce this down a little bit. So I see two molecules of this ICl. So I can rewrite that instead of writing them each individually. I can say I've got two of those ICl molecules that I need to use. And then same thing over here. I've got two HCl's that get produced. So instead of writing them individually, I can say I've got two HCl's that I need to produce. Okay. So elementary steps, identify intermediates, get rid of them, and then add together the two reactions. That gives you your overall reaction. So this is the same as that guy right there. Okay. And of course, I've got this in the slideshow, reaction intermediates. Okay. So just a little bit of terminology before we move forward with this chapter. The number of reactants, particles involved in the elementary steps, they tend to have names. So if there's just one reactant, so this could be something like 2 molecules of water break down into H2 plus O2. Okay. So this would be an example of a unimolecular. We've got one reactant as our, that's not a good example. We've got one thing as our reactant. So if H2O breaks down, we've got one reactant. It's a unimolecular. Here, if we've got 2 particles, that would be a bimolecular. So actually the example I just gave you is a bimolecular. So we've got 2 molecules of water breaking down. Another way of writing that is an H2O plus an H2O. So A plus A or H2O plus A2O, that's a bimolecular. And then we could have another example of a bimolecular where we've got 2 different kind of reactants. So we have H2 plus O2. That would be an example of a bimolecular. Trimolecular does exist, but it's really, really hard to get 3 different particles to line up in the correct fashion with the correct energy to produce some sort of product. So by far, unimolecular and bimolecular are the most popular for elementary steps. Trimolecular exists, but it's few and far between, so we won't talk about it. Okay. We can look at the rates of a unimolecular and a bimolecular. So if it's unimolecular, we just have one of our reactants. The rate law would just be rate equals K, and that would be a first order reaction there. If we've got a bimolecular elementary step, so we can't use this for an overall reaction, we'd have to look at the data. But if we've got a bimolecular elementary step and it's A plus A, we can assume that that would be a second order. So we can put that squared up there. And then a bimolecular where they're different, so A plus B, we can assume at the elementary step level that those are each first order reactions. So this is going to be important when we start to look at the mechanism, is to remember that in the elementary step, I can look at an A plus an A and say that that's second order. Or I can look at an A plus a B and say that's first order and first order. So it'll be important that we can do that. Okay. So as I talked about before, there's going to be a step that's called the rate limiting or rate determining step. So the rate limiting or the rate determining step is going to be the reaction, the elementary step, the elementary reaction that's much slower than the other ones. This is not going to be something that I have you guys memorize. It's something that's always going to be given. So I'll either give you the rate of the reactions and you'll be able to use the numbers to determine what's slower, what's faster. Or I'll simply say fast, slow. So I'm not going to have you memorize any reactions as being fast or slow, okay? But the rate determining step or the rate dependent step is always the slow step. So let's look at a reaction here. So our overall reaction is the reaction that you see highlighted on the screen. So nitrogen dioxide reacts with carbon monoxide to produce nitrogen monoxide and carbon dioxide. So this is our overall reaction. This is the one that we observe. This is the one that we're interested in. Okay. Here are the elementary steps in this reaction. Okay, so elementary steps. The first step is slow. The second step is fast. So what this tells me is that the rate of the overall reaction is going to be limited by that first step. So for these 2 molecules of nitrogen dioxide to react with one another, that's going to take a while. It takes some time. So slowly, these 2 are going to react. And slowly we're going to start to produce these two intermediates. Okay, well, this one intermediate. Okay. This guy right here is our intermediate, NO3. It's not in the overall reaction. We're going to immediately consume it. So as NO2 slowly reacts with one another and starts to produce this NO3, NO3 is very unstable. Okay, that's a super, super unstable molecule. So the minute that we start piling a little bit of this NO3 up, immediately that's going to see this carbon monoxide and say, I'm going to make a reaction with you so that I can become more stable. So as soon as this starts piling up, boom, it immediately reacts with carbon monoxide to create this. That's a fast step. Okay, we get NO3, carbon monoxide, those react together pretty quickly. So this overall reaction is going to be limited by this first step. This is what's going to slow us down. Once we get this intermediate formed, then everything's going to go pretty quickly from there. Okay. So let's take a look at what a rate determining step looks like from an energy perspective. So here is our energy profile. So up until this point, we looked at energy profiles like this. Here's our reactants. Here's our products. And we've got this activation energy. And then once we establish that activation energy, then we can slide down to our products. When we have these elementary steps, what we're going to see is a couple different things. The first thing we're going to see is we're going to see two humps happen, right? So there's an activation energy for this step. There's an activation energy for this step, okay? So there's going to be a hill that needs to be surmounted for each of these steps to happen. The rate limiting or the rate determining step is going to have the higher activation. The higher activation energy, okay? So if we were to look at this energy profile and I said, well, which step is the rate determining step? You can determine that by saying the one with a higher activation energy. That's the rate determining step. Okay. So that's the first thing that we want to look at is this energy profile. Okay. What can we do with this information? The elementary steps in a mechanism can sum up to the overall reaction. So we talked about how to do that. We identify reaction intermediates, this NO3, and then we add up everything that's left, and this is our overall reaction. Okay. The rate law can be predicted by the mechanism. So if we know the elementary steps, we don't necessarily have to do the data collection to predict the rate law. So if we know the elementary steps, we can predict the rate law based on those elementary steps, based on the rates of each of the individual steps, okay? And this will be consistent with the experimentally observed data, okay? So how can I predict the rate law based on these elementary steps? Okay. So to determine the rate law based on these elementary steps, here's what I do. This is the slow, this is the fast, okay? So the rate is determined, the rate is predicted by the slow step. Once I get past that step, then everything goes quickly. So here's what the rate looks like. Rate equals K. And if the first step is the slow step, then the rate is just whatever the reactants are. So NO2, NO2. Okay. So if the slow step is the first step, we just simply write down the rate law based on the reactants. Now, remember, I can clean this up a little bit. So since NO2 and NO2 are the same, then I can say, oh, I bet this is a second order reaction, and it is. Okay, so this is the rate law of this overall reaction based on the information that these are the elementary steps, and the first step is a slow step. So anytime on a quiz, exam, whatever, if the first step is the slow step, you should go, woo, hallelujah, that's an easy one, and just write the rate law down based on that step. Things start to get trickier and more difficult when the slow step is not the first step. All right. So what if? What if the initial step is fast and the slow step occurs later on in our elementary steps? Well, that's when things are a little bit more difficult. What tends to happen when the first step is fast is our rate law, if we just simply write it based on the slow step, our rate law contains intermediates, and that cannot happen. If our experimental data rate law and our predicted rate law have to match, if it has an intermediate in, it's never going to match, right? So our rate law can't have intermediates in it. So we have to take care of that first. The initial step may enter equilibrium. So we'll look at that in just a second. If that first step enters equilibrium, we can use that K value for that step to help us determine the rate law. So once we address the intermediates, we use this idea of an equilibrium to help us determine the K value. So we'll see that in just a minute. Okay. So here is our example. So here is the overall reaction. So nitrogen monoxide reacts with bromine to produce two of these big old molecules right here, NOBr. Okay. Through experimental data, I have determined that this is in fact the rate law for this reaction. So I know the answer already. We're going to practice this skill of using the mechanism to get back to this. So essentially, I've given you the answer, but we're going to learn how we can get to that answer, okay? So here's our proposed mechanism. Here's our proposed elementary steps. So step one, we have one molecule of nitrogen monoxide reacting with bromine to create this intermediate. So the intermediate has two bromines on it instead of just the one, okay? This is a fast step. This happens pretty quickly. The second step is our slow step. So in order for this guy to come in contact with another molecule of nitrogen monoxide and create two of these, so for one of those bromines basically to come off and attach to this one, that takes a while, okay? So that's a little bit more difficult. That's our slow step there, okay? So right away, slow step is the second step. Red flag should be going off. This is the more difficult problem, okay? The other thing I want to point out here is this double-sided arrow. So we're going to see this at length in the next chapter. But what this double-sided arrow tells me is that this reaction is going forwards and it's going backwards. So pretty quickly when I mix these two molecules together, I start to get a bunch of this pile up. And as that piles up, some of it is going to start to decompose back into the nitrogen monoxide and bromine. So because this second step takes a while, this guy is going to start to decompose back into where it came from, okay? So a dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, and we'll see why this is handy to know in just a minute. So that's what this double-sided arrow means, okay? All right, so if the rate law is determined by the slow step, I should be able just to say that rate equals K times NOBr2 times the concentration of NO. Okay? But what's the problem with this? Well, yeah, first, it doesn't match this. So this is what I determined experimentally. And these two are not the same. Okay, so that's the first problem. The second problem is, what is this guy right here? What is NOBr2? Yeah, it's a reaction intermediate. Okay, so this is an intermediate. We produce it in one step, we consume it in another step, and it's not found in the overall reaction. So intermediates do not belong in our rate law. So if that doesn't belong in our rate law, how do we get rid of it? Okay. Well, that's where this comes in handy. Okay. To get rid of our intermediate, we need to find out where our intermediate came from. So our intermediate came from step one. So we look at where it came from, and we look at the K value associated with that. Okay. So here's what we had before. So our rate law equals that K2, this the K for the second reaction. There's our intermediate. We want to get rid of that. Well, where did our intermediate come from? It came from this reaction. Oh, that's not concentrations. It came from this reaction. Okay, so in order to get rid of that from our rate law, we need to determine, well, where did that come from? So we're going to go back this way. So I'm just replacing this intermediate with the reactants that it came from. So it came from NO and it came from Br2. So we just replace those. But with that comes its own K value. So, whoopsies. With that comes its own K value. So NOBr2 is what replaces it, but that has a K value of K to the -1, or the reverse of K. So if this way was K1, this way is K to the -1, the inverse of that, or the reverse of that. So when I put in our reactants to get rid of our intermediate, I have to also put in that K value, okay? So our new rate is going to be rate equals, and the K, I've put a little asterisk here, okay? So the K for this value is complicated. That's what that asterisk means, okay? And we'll get to that in just a second. And then I put in my reactant, and then this is carried over from the first one. So that's carried over from here. Okay. All right. So K asterisk. K asterisk is telling me this right here. And I'm actually going to change this. Instead of being K to the 1 over K, I'm going to say K to the -1 times K squared. So this K asterisk, we need to acknowledge the fact that there's two different K values that we're interested, or two different K values that are associated with this rate law. So that K asterisk addresses that right there. Okay. This can be cleaned up a little bit more. So we've got NO and NO. So instead of having those as individuals, I can say that this is a second order, or this NO squared times Br. So this is the rate law associated with the reaction. And what we see is that is exactly what was predicted. And this is K asterisk, where K asterisk equals K -1 times K2. Okay. K -1, K2. All right, so that's why I say when you see slow step as the first step, you should say hallelujah, because fast step as the first step is hard. So what I want you guys to do here, this one has 3 elementary steps, so a little bit more difficult. 3 elementary steps. So what I want you guys to do here is predict the overall reaction and then predict the rate law for that reaction. So go ahead and pause the video and then I'll work through it with you in just a moment. All right. So first things first, let's identify our intermediates. Okay. So step 1, I produce this into O2. Step 2, I consume it. So produced, consumed, that's an intermediate. Okay. In this next step, I produce water, but water's not consumed anywhere, so that's fine. And I produce this N2O, and I consume it right here, okay? So N2O, produce, consume, that's also an intermediate, okay? So let's go ahead and predict this overall reaction. So what's left over here on the reactant side from step 1 is 2NO plus H2 plus H2, okay? And we can clean this up. There's 2 molecules of H2. Good. So product side, I've got water from here plus into plus H2O, okay? And again, I can clean this up. I've got the 2 molecules of water there. So clean this up a little bit, and I can do 2 molecules of water plus nitrogen, okay? So that's the overall reaction there. The hard part here is let's determine the rate. So before I do that, I do want to put some K values, so we'll just call this K1, K2, K3, okay? All right, so rate is determined by the slow step. So it's determined by this guy. So rate is going to be K2 times H2 times into O2 concentration. Okay. So that's going to be the rate law. I chose this one because that's the slow step. That's my rate determining step. But what's the problem? Yep, our rate law cannot have an intermediate, okay? So now I need to decide where did this come from? Because it's an intermediate, it's not going to be in the overall reaction. So when I look at the first step, I see that N2O2 is a result of NO reacting with NO, okay? So I'm going to replace this with where it came from. Okay, so I'm going to replace this with NO, NO. But with it comes what? Yeah, there's a constant associated with that step. So with this is going to be K1, actually negative 1, because we're going backwards, NO, NO. Okay. So this green replaces our intermediate with something that is found in the overall reaction. So now we need to clean this rate law up down here at the bottom. Okay, so up until this point, we've got rate equals K2 times H2. And then we've got K to the negative 1, NO, NO. So I just copied what I had in the previous slide. So now to clean this up, I want to write the rate of the overall reaction. So rate equals and we have a messy K. So K asterisk, H2, and then I'm going to combine these two. So NO, second order. And then I'm going to have my little disclaimer over here where K asterisk is K2 times K negative 1. Okay. These are cursive Ks. I know that confuses people for some reason. Okay. So this would be the answer to this question. So that's it on reaction mechanism. So big take home here is the rate is determined by the slow step or the rate determining step. If the first step is the slow step, then it's really easy. We simply write down the rate law based on that first step. If the slow step is the second or the third step, usually it includes an intermediate. So I'll have to do just a little bit of extra thinking to get rid of that intermediate and make sure that our overall reaction and our rate law match. I hope you guys found this helpful.